So say we had a argument that used predicates rather than just regular old propositions. Well, turns out there's also a set of rules that have, or a set of rules that are specifically for predicates, and you can see them right here. First, you have your universal instantiation rule, which when you have a for all x, p of x, you'll imply p of c, and this will just be any old statement, but this will be your original statement. And then say you have a universal generalization. That's what this is, just a general statement of p. Say you just have this will then switch back to this when you need to. And then the same thing when you have the existential quantifier. You can, if you have for some, I guess for at least 1x p of x, it will instantiate generally to this statement. And then say you wanted to go back to this one, then you just use this rule, and they all work very well. So let's go over an example for while using predicates. So I have this argument here. Everyone in the class likes ice. Everyone that likes ice cream likes chocolate. Everyone either likes Belgium or does not like chocolate. Someone at Carleton likes ice cream, therefore at least one person in Carleton likes Belgium. Okay, so first of all, let's split this into the predicates that they are. So right here we have a statement, everyone that likes ice cream. So we can say here that likes ice cream is a statement, and we're going to call that c of x, Okay, and then we also have a statement here that's everyone that likes ice cream likes chocolate. So likes chocolate is also its own statement, so that's h of x, we'll call that. Now, everyone either likes Belgium or does not like chocolate. So we have a statement here that says likes chocolate, so we don't have to worry about making a new statement for this. It's just not h of x. But here, everyone either likes Belgium. So likes Belgium is its own statement. And we'll call, well, whenever it decides to write it, we'll call this b of x. And then someone at Carleton likes ice cream. So at Carleton will also be its own statement. And finally here we have our conclusion, and you can see the statements are being used. At least one person at Carleton likes Belgium. So those are all our predicates that we're using for our statement. Okay, so let's now show that this argument is in fact valid. So first of all, let's just write out our different premises that we have. So first of all, we have c of x. Oh, first of all, we have, it says everyone, so we have to write our for all statement here. That we have everyone that likes ice cream likes chocolate. So when we have a universal quantifier in front of a statement like that, we have to make sure that we're implying that everyone that likes the ice cream also likes chocolate. Now, our next premise here is everyone either likes Belgium, so b of x, or does not like chocolate, so that's not h of x. Okay, that's our next premise. And then finally we have our last premise, so someone, so that's someone like this, so that's just one person, at least one, at Carleton, so c u of x likes ice cream. And when you have a existential quantifier like this, you always have to put an and in between your two premises. So sorry, your two predicates. So that's someone at Carleton likes ice cream. So that's c of x. Cool. So now, what is our end goal? What is it that we want to show at the end? Well, our conclusion. So it says, therefore, at least one person, so we know that there's an existential quantifier there. At least one person at Carleton likes Belgium. So we have to write that at least one person at Carleton, cu of x, likes Belgium. So there you go. We've written out our premises and how they lead and what conclusion we want to lead to. So now let's show that this actually does lead to that conclusion. So first thing that we should do is take this statement. Why? Because it's a very easy statement to simplify. So let's look at for some x, u of x and c of x. Okay, so first let's use an implication, a predicate, one of these predicate rules on it. Why not use this existential instantiation? Because we can. So let's change this statement into something simpler. So cu of a and c of a. Okay, so now we're just down to two predicates like this. Now we can use our rules of interference again to simplify this down. If we go back up to our rules of interference, we can see we have this simplification rule again that we can apply on this. And so that makes this a cu of a. Okay, and that's going to be useful to us because we have to show cu of a and b of x. We have to show this statement at the end, and it involves a cu, so it's useful to us. So what's the next statement that we can? What's something else we can do now that we have our cu of a? Okay, so let's look at our different statements here. We have b of x or not h of x, and then we have c of x implies h of x. Okay, so I think we can maybe do something a little clever here. So I'm going to use this statement, right? And I'm going to say that right here, I'm going to do this right here. For all x, c of x implies h of x. Okay, now I'm going to do a universal instantiation on this. And now remember, a is just our general statement here, so I can use c of a implies h of a on this one as well. It's not like in the rules they might have different things here, but it's actually just a general statement. So you can really use anything there, right? So now, what can I do? I think I'm going to do another simplification on here, right? Because, see, we have a c of a here and a c of a here. So I think we can apply a rule to this afterwards. So let's do this. We have a simplification again of statement 2. So this simplifies to c of a. And we can now go up to our rules again. And I think we can use a modus ponens on this. Why? Because now this whole statement right here becomes just h of a. Cool. Now, why would this be any use to us? Because, hey, we have a not h of x right here. So let's actually do a universal instantiation on this as well. Okay? So our statement 8, we have for all x, b of x, or not h of x. Okay, let's do a universal instantiation on it, so it becomes b of a or not h of a. Cool. So now what can we do to simplify this down even more? So we have a not h of a. Let me get rid of these brackets so it's not as confusing. We have a not h of a and a h of a and a b of a. So let's go up to our rules and see exactly what we can use here. Right here, we have a disjunctive syllogism. We have a p or a q with a not p. So right here, you can see that we have our not h of a and our h of a. So our disjunctive syllogism applies here. So that states that we can now simplify this down into just b of a. Okay. So now, what can we do? Well, we have here, we already used a simplification rule on this one, so we have a CU of A. And right here we also have a B of A, which I think that fits into our criteria right here. So let's use another rule on this, and if you go up you can see we can use a conjunction rule to make this a to put an and in between those two. So we can make it a CU of A and a B of A. Oopsies. B of A. Alright, so now let's use a universal generalization rule. So we're changing our general statement back into our regular statement, except we're not using universal, we're using existential, that's my bad. Existential, and this becomes CU of X and B of X. And there you go. We've just shown this is a valid statement.